Hi everyone, and welcome to our last lecture for this course. In today's lecture, I'm going to be going over a final overview of what we've done throughout this semester. I'm going to be splitting up this lecture into two sections. In the first one, I'm going to be doing a conceptual overview of all of the things that we've seen. And then in the second section of this video, I'll be going over the different types of notions and problems that you need to have mastered and know how to solve in order to succeed in this course's final. So let's get started. First off, a conceptual review. My goal here is not to introduce any new things for you to learn or anything of the sort. My goal is to try to tie together everything that we've seen in this class. And I've told you several times that this course is roughly divided into three parts. Part 1 covered functions. This was the focus of your first exam in this course, and this was roughly the content of Chapter 1 in the textbook. Part 2 covered derivatives. Derivatives are covered in chapters 2 through 4 in the textbook, and I'd say that part 2 is definitely the meatiest section of this course. It is what we spent the most time on, and it is what we went into the most depth for. Last but not least, we have part 3, and we didn't do too much in part 3. Most of this material was covered after spring break, so this was in the online lectures portion of this course. But part 3 covers integrals. Now, if you were to take any more or any further mathematics education at the college level, so if you were to push your calculus learning any further, you would definitely cover a lot more when it comes to integrals than we have in this class. But for this class, we've just sort of touched on them, we introduce them, we introduce one advanced technique for those, and we don't go into too much further detail. Now, before I go into any further detail about any of these three parts that our course took part in, I want to do one quick sort of comment on the way that I view mathematics and the way that hopefully I can get you guys to at least somewhat see math as well. And the key thing here is that math is all connected or interconnected. It is very easy to learn math as a bunch of separate different notions or different ideas, different definitions, different techniques that don't necessarily have much relation to one another. But really, everything in math, in some sense, is related to everything else. Some of it is related more closely than other things, for sure. But overall, I think the best way to understand mathematics, even mathematics at the level of our course, is to view that all of these parts are connected to each other. And this is what I'm going to hope to at least show you guys, even if it's only a little bit today. Now, what I'm going to do for each of these three parts is I'm going to go over, first off, all of the concepts and ideas or topics that we covered, and also go over what the point of this is. Our class is not a pure math course. It is not designed for mathematics majors or even necessarily for STEM majors. The goal of this class is really to get at some sense of applications, especially to real life. So I'm going to try to really make clear what the purpose of all of these concepts are for each of these sections. And hopefully I can also give you guys a little bit of an idea of how all of these ideas or notions that we covered in these three different parts of this course sort of tie together and tie into each other in a very nice and sort of very helpful way. All right, so let's get into this with part 1. Part 1 covered functions. And as I mentioned, we're going to be splitting this up into material / topics covered on the one hand, and on the other hand, I'm going to go over applications / I'll say purpose. Okay. In this first section of our course, we went over a bunch of different topics. Most of these were just different types of functions. And we went over each of these individually. We covered linear functions and linear models. We covered exponential functions. We covered logarithmic functions. We covered power functions. We covered polynomials. In a different calculus course, there might also have been some other types of functions added to this list. Particularly trigonometric functions might also have been added, but we did not cover any trig in our class. We also covered different models. And properties. And we covered, finally, function composition. These are the topics that we went over in the first section of our class. We covered a bunch of types of elementary functions, linear functions, exponential functions, logarithmic functions, power functions, and polynomials. Then we covered, for each one of them, well, for some more than others, we covered how you can use them to model certain very basic events or phenomena in real life. And last but not least, we covered how we can combine these functions using a technique called function composition in order to create new functions that are more complicated, perhaps a bit more fancy, definitely a bit more difficult to work with, but just by using these component pieces that we learned previously. That's the list of topics or material that we went over. But what I want to make clear here is give you guys an idea of why does this stuff matter? There are several reasons. The first reason why these things matter is that we were going to, and in fact we did, have different rules as far as derivatives and integrals for each function type. We also had a rule for composition. For derivatives, we deal with function composition by using the chain rule. And for integrals, we do it with integration by substitution. That's a very practical reason why this course started by covering these types of functions. The reason why we spent so much time at the beginning of this semester going over linear functions, exponential functions, logarithms, power functions and polynomial functions, as well as these ideas of function composition. The real reason, as far as the course is concerned, as to why we covered all of this, is because for each of these different types of functions, we were going to need different rules for finding their derivatives or integrals. We went over things like function composition, because for that too, there are special rules for both derivatives and for integrals as to how to deal with those. Now, this is still a very, very practical overview of why we covered the material that we did. Right? This is a very sort of self-interested sort of rationale, where we're really just viewing it from the perspective of this class on its own. But there's a bigger reason as to why we cover functions, and more importantly, why you guys should care about functions even outside of this course. And this is very simple. Functions are used to model real life. We covered a little bit of this in our class as far as different types of things that you can model with each of these. I'm going to do this in a slightly different color. Linear models, we covered revenue. We covered cost and profit. We viewed that all of these business notions can be, in a very simple way, modeled using linear functions. For exponential functions, we saw that this models radioactivity. And also models population growth. As well as even drug elimination. All of that was just different types of exponential models, and these are all sort of very simple, very straightforward. Oh, I actually forgot one. From the business perspective, exponential models also give us interest. That's arguably the most important one of these, so it's important that I not forget that. All of these things can all be modeled in a very straightforward way using exponential functions. So even if you ignore all of the calculus part of this class, even just those two types of functions, linear functions and exponential functions, can give you an idea of how a lot of really important day-to-day stuff actually works from a more quantitative perspective. And I think that that's really important. Now, there are some things that we didn't necessarily cover in this class, or if I did, it was sort of very, very, perhaps in passing. And you might think of logarithms as a strange tool, but actually logarithms show up quite a bit. Did you guys know that decibels, the unit of sound, is actually on a logarithmic scale? They're measured using a logarithm. So it's actually not a linear function of how loud or how much energy there is in the noise. It's a logarithmic measure of how much energy there is in the noise. Did you guys perhaps also know that the Richter scale for earthquakes is also a logarithmic scale? That means the number that you see, if you see that an earthquake was 5.2 on the Richter scale, and another earthquake was a 6.2 on the Richter scale, that jump from 5.2 to 6.2 is actually done on a logarithmic scale. That means that a 6.2 earthquake is actually 10 times as powerful as a 5.2. And you might not realize that just by listening or just reading about this in the media, but that's because the Richter scale uses a logarithmic scale. This stuff shows up in real life, and it's not necessarily super obvious or super evident at first glance what it is that's going on until you realize that you're working with logarithms here. Okay, so that covered the different topics that we went over in this section, and sort of the rationale behind why we went over this stuff. But this still doesn't sort of tell us exactly what it is that you need to understand. And I use the word understand here and not the word know. This is not something that you need to know. This is not something that you need to memorize. This isn't something that you're going to be super quizzed on, or that there even is a very good way for me to quiz you on as far as our material goes. This isn't what you need to learn for a test or anything of the sort. This is instead what I'd like you to understand about this section and about what we did. Now, the first thing I'd like you guys to understand from this section is that functions capture a relationship between two quantities. An input, often written x, and an output, which is often written y. That's all functions are. They just capture some form of very standard or a rational relationship between an input and an output that has some sort of meaning behind it or some sort of connection between these two. The second thing I'd like you to understand about this is that functions can be described in different ways. Each with pros and cons. Now, we went over this pretty sort of in depth when we originally went over this section, but I think this is something that really gets lost in the mix of things and is easy to forget since we only went over this very early on in the course. Now, the first of these ways to describe a function, let's call it little a here, is graphically. Now, graphically, to graphical representation, there are various pros and cons here. Pros is that this is very visual. You can actually see what the function looks like. You can see whether it's going up or down at just a glance. You can see where the high points, where the low points of the function are. Humans are very, very visual in general, and so having some sort of visual representation of this information can be very, very useful. Now, just the visual aspect is not the only benefit to representing functions graphically. You can also have applications to geometry. For example, did you guys know parabolas, yes, the shapes that are described by, say, f of x equals x squared, did you know that those have geometric properties that make them very, very nice as the shape to use for satellite dishes? They're also the shape that is used in the headlights for your car if you have one. That's because they have geometric properties, and you can sort of figure out these geometric properties in part by representing these functions graphically. There's a lot to do there. Now, a second way to describe functions is by making a table of values. The pros of using a table of values are that this often represents data points. And if you want to know what I mean by that, what I mean is that oftentimes in real life, the data that we gather about a phenomenon is actually what we call discrete data. That means that we don't have data for every moment of time that's ever taken place. We have sort of data from, say, the year 1991, data from the year 1992, data from the year 1993, etc. We have point-by-point information. And tables of values represent this information about the function in that point-by-point way. You also have numbers. at a glance. So those are different advantages of the table of values way of doing this. Oftentimes in real life, like I mentioned, the actual data that you're getting, if you're running some sort of experiment, or if you're trying to do some form of analysis, say you're running a business, and you want to analyze how well your business or how efficiently your business has been doing something, say in the marketing front or something of the sort, oftentimes the information that you're going to get in your analysis is going to come in the form of a table of values. And so that is the most honest way of representing that information if you're trying to relay it to someone else. I'll get to the cons in a moment, but first let's cover the other ways of doing this. So the third way is with a formula. Say f of x equals. This is often what we focus on in a math class. And this is also, for many people, the most confusing or sort of arcane, weird type of way of looking at this information or working with it. But there's a very important pro to using this, is that this is plug and play. It is accurate. And it is easily manipulated. So for example, if we're taking derivatives or integrals, oftentimes having the function in the form of a formula is the easiest and most straightforward way of working with it. That's the way you want to do this. Last but not least, the final way that we choose to represent function information is verbally. And verbally, what I mean by this is a description of the relation. And a big pro about this is that oftentimes here you can use layman's terms. And also, and this is very important, verbal representation of this information can allow you to develop an intuition for what's going on. If you're able to look at a function given to you as a formula and describe verbally what this function is doing, that means that you have some form of intuitive understanding of what it is that's going on, even though the information is presented in a very mathematical way. All right. As I mentioned, all four rather, of these types of, or different ways of describing functions, all are valid, all are important, and all have different pros and cons. I've written some of the pros here, but let's also go over the cons of these. The cons of the graphical representation of information is that oftentimes reading off data is imprecise. And this is also very hard to manipulate. It's very, very hard to work with just a graph on its own. Even though you can read off values, that's imprecise, and it's difficult to work out what a derivative might be, or even add it to add two functions together if you only have them graphically. That's not particularly straightforward. It's sort of difficult to work with graphically described functions. However, oftentimes if you're trying to just understand or relay the information, working graphically is very useful. The cons of a table of values are obviously that they are incomplete, which is a problem on its own, right? You don't have all of the data, you just have point-by-point information. But the other more I'd say, insidious issue with tables of values is that you can have fake trends, right? Just because you have a table of points from a function, that doesn't mean that what's going on in between those points is following the same trend as the points themselves. So if you have a small table of values, or maybe somebody cherry-picked the points from a function, they can actually use this to mislead you about what's going on, right? Because you don't know what's going on between points, tables of values can sometimes be misleading or make you think that there's a trend going on that doesn't actually exist. All right, the cons of working with a formula are pretty straightforward. The cons are that it is, how shall we say, unintuitive, or sort of, I'll say sort of obscure or opaque information. And what that means is that you don't just at a glance, unless you have a lot of training, like for example I do, you don't necessarily at a glance have a very clear idea of what's going on with the function until you do more tests with it or represent it in a different way. So formula is very easy to manipulate. It's very easy to plug in information accurately, but it's hard to tell just by looking at the formula what's going on. In a sense, this is the opposite of representing a function graphically. Graphically is very clear, you can see right away what's going on, what the trends are with the functions, but it's imprecise and difficult to manipulate. Formulas are very accurate and very easy to manipulate, but it's unclear at a glance what's going on with your function. And last but not least, the main cons with representing things verbally is that you can't really do math. At all with a verbal description of a function. You have to transform verbal information into formulaic or graphical information to be able to do math. Now, I'm almost done with part 1, but there are still a couple more things that I'd like you guys to understand about what we covered in this section. All right, I'm going to get rid of this and pick up where we left off with number 3. The third thing that I'd like you guys to understand from this section is that functions are models. Of real life. And what I mean by this, and more importantly, the way that this process of modeling things works, is that it goes as follows. So first off, what you do is that you develop, or you find, a function that appropriately captures or describes the phenomenon that you're trying to work with. Right? First thing you have to do is you have to figure out what function is it that properly models what you're working on. Step 2 is perhaps not as immediately obvious, but the key thing is that step 2 is to learn or analyze the properties and techniques that can be used on or with these functions. And the third step is to reinterpret the results of this analysis in real life terms. This is the methodology that we use, and it's not always obvious that this is what we're doing. And the thing I want to point out here is that this step 2 here, this step 2 is what I like to call using your math toolkit. A lot of people, and I know I come back to this very often, a lot of people ask either themselves or each other, or sometimes even they ask their instructor directly, why is it that we go through all the trouble of learning all this math? Why do we learn all this stuff? Why do we learn calculus? Why do we learn about functions? Why do we learn about, the laws of logarithms, or, the all the stuff with the y-intercept and the slope and all that for linear functions? Why do we learn all this stuff? Well, what we're developing in a math course is what I like to think of as a toolkit. And I do mean that just like a carpenter's toolkit that has maybe a saw, a hammer, different types of drills or screwdrivers. We have all these different tools in a toolkit. And in the same way in math, you also develop all of these different mathematical toolkits. We use these tools to analyze, break down, and manipulate the functions that we found that we have decided or discovered or developed to describe some real life phenomenon, right? We take a real life phenomenon, we turn it into a function, and then we use our big math toolkit to figure out everything that we need to know about this function. We figure out what its maximums are. We figure out what its rates of change are. We figure out whether it's increasing or decreasing. We figure out whether it's accelerating or decelerating, which is different from increasing or decreasing. And that means the same thing as figuring out whether it's concave up or concave down. We figure out where its inflection points are, right? We figure out what the general behavior of the function is. All these different things, we use our math toolkit to figure this information out about a function. And then the third step is, why did we do all of this? Well, now that we have all this information about the maxima and all that stuff, we can reinterpret all of that stuff in terms of real life, in terms of the phenomenon that we were trying to look into in the first place, right? If you turn your business model, something about your profit for your business model, into a mathematical function, you can figure out what its maximums and minimums are. That alone tells you what are the points that make you the most money and the least money. That's really good to know. This is the process that we use with functions. This is why we care about functions, and this is the idea behind modeling. This is actually the whole goal of this course. The whole goal of this course is to develop this second step in the modeling process, and to add to the toolkit the tools of calculus. That's what we did here. We took this toolkit and we added to it the tools of calculus. And that was in parts 2 and part 3 of our course, which I'm about to get into. Okay, I know I spent a lot of time on part 1, but everything that I just went over from part 1 carries on into part 2. And part 2 was derivatives. Now, like I said just earlier in part 1, and like I mentioned, everything here is interconnected. Please don't view these as separate, completely different, unrelated things. All of this stuff connects with one another. Part 2 with derivatives is at first glance just adding a new tool to your mathematical toolkit. Okay, now let's get into the material and topics. That we covered. And what this time I'll call the interpretation. And application. Of this material and these topics. Okay, so the first thing that we covered was a definition of the derivative. Okay, and we said basically that the derivative is the slope of the tangent line. Then we went over a bunch of derivative rules, right? And I break them up into the basic rules, which are power rule. They are exponential rule. They are the log rule. They are the sum rule. And the constant multiple rule. We went over these very sort of basic rules. And then we went over the advanced rules. Which are the product, the quotient, and the chain. Those are all the rules that we covered. And we just did basically a full chapter where the only thing that we did is learn rules for calculating derivatives. That's basically all we did. And the last thing that we did for the last sort of major section of material from part 2 in derivatives was that we went into applications. So we saw optimization, which involved critical points, maxes, mins, and then we also went through things like concavity, etc. So this is a very, very sort of high-flying overview. And the reason why I'm doing a very high-flying overview here is that, like I mentioned when I was going over everything from part 1, all those things from part 1, the reason why we went over power functions, exponential functions, linear functions, log functions, polynomial functions, the reason why we went over all of this, the reason why we went over function composition, is that all of those things corresponded or ended up corresponding to rules that we needed to go over for finding derivatives. So each of these basic rules that you see over here, all of these basic rules corresponded to one of the types of functions that we saw in part 1, and this chain rule over here corresponded to the function composition technique that we also learned in part 1. Okay. Now, what about the interpretation? Why did we learn about all of this? Is that, first of all, derivative is speed. Or rate of change. And this is very important information about real-life phenomena. Right? These tell you about trends. You know? Are you trending up or down? How fast? The derivative tells you about this, right? This is all the interpretation, the reason why this finds applications to real life, is that whenever you'd care about speed, how fast some phenomenon is changing or anything like that, that's where you can use this new tool of the derivative. You know, once you have a function that describes or models the phenomenon you're working with, the derivative allows you to tell you something about the rate of change, about the speed of this phenomenon in a very straightforward mathematical way that you can reinterpret in real life terms. Why do we go over the rules? You know, you might ask yourself, okay, But why do we take all this time to go over the rules? Well, the reason for this is that, well, I'm going to be honest with you guys. In our class, in our course this semester, we didn't really go over the real definition of the derivative. We sort of very glossed over the very sort of basic nitty-gritty, super nitty-gritty way that mathematicians like me use to define the derivative. It's a weird thing. It involves limits. It involves something that's called infinitesimals. And it's a big mess. If you were to take a full calculus course, you would actually learn a bit more about this stuff. Now, the reason why we go over all of these rules is that these rules, they actually make derivatives easy. You may or may not believe me here. I understand this. Right? For a lot of you, derivatives might not be that easy. They might be pretty difficult. And that's fine. That's not what I'm talking about when I say easy. I'm even going to put this in quotes. The reason why I say easy is that I'm saying this is easy compared to what's going on behind the scenes. So what I mean by this is that for all of these derivative rules, there's actually some mathematician guy, kind of like me, who came along someday, and he used this really weird, funky, very difficult definition, basic definition of the derivative, and he smacked each of these types of functions. He smacked power functions, or she smacked power functions with this rule. They smacked exponential functions with this rule. They smacked logarithms with this rule. They smacked sums of functions with this rule. They smacked constant multiples with this rule. They smacked products of functions with this rule. They smacked quotients of functions with this rule. They smacked, compositions of functions with this rule, or with this definition, rather. They did this. They did all of the nitty-gritty work, and at the end result of what they got was this rule. For power functions, they ended up with the power rule. For exponential functions, they ended up with the exponential rule, and so on and so forth. So somebody came along and did all the hard work for you. They did all this hard work so that you could get an easy, at least relatively speaking, rule for each of these situations that you can apply and use in order to find derivatives without having to worry about all of that infinitesimal stuff. You can throw that or hide that all behind the scenes. Let mathematicians like me deal with that. Instead, you just use these rules of derivatives, and you can find derivatives yourself without needing to be a mathematician who's learned all this stuff about what we in mathematics call mathematical analysis. You don't have to know any of that to be able to find derivatives. And that's really cool. That's really useful. That in itself is a reason to cover these rules. That's the whole point of the game here. Now, last but not least, optimization. I almost shouldn't have to tell you guys what the interpretation or application of optimization is that finding the high points or the lowest points is very useful. So this, very, very globally speaking, is an overview of everything that we covered. Now, obviously, as I said, Part 2 is the meatiest section of our course. So it might seem sort of weird to have spent in this video less time going over all of this derivative stuff than I just did in Part 1. But the reason for this is that even though this stuff fits in this small table here, the actual amount of time that we took to develop all of these rules, to develop the definition of a derivative, to develop even the definition of a tangent line, and to go over all these ideas of optimization, obviously took quite long, and even longer than it took to go over all of the materials and topics from Part 1. So even though this is a small list of things, the things themselves took quite a while to go over, explain, and work through. Now, even so, the interpretation of this is really important. Whenever you see a derivative, we're talking speed here. That's what derivatives are about, right? That's what they're used for, to find trends of things, right? And the reason why we did rules, like I just mentioned, is that rules actually help us save a lot of time. They allow people who don't have to learn very, very high level mathematics stuff to actually do some calculus and actually reap the benefits of knowing about derivatives. And the whole purpose of optimization, like I mentioned, sort of speaks for itself. Optimization is about finding maxes and mins, and there's so many situations in real life where if there's a phenomenon that you are interested in, you often want to know what its highest and lowest points are, whether that's making the most money that you can, or minimizing the downsides or side effects of a treatment in a medical scenario or anything like that. Maxes and mins are often super, super important to know about when we're working with real-life phenomena. Now, with this said, let's go over what it is that I'd like you guys to understand. And the first thing that I'd like you guys to understand is that derivatives are both, on the one hand, a tool. That just means it's just a tool that you should be using. It's a tool that belongs in that mathematical toolkit that we were talking about earlier, and themselves a topic of interest. And the reason for this is that derivatives are the speed. That's what they are. This is super important. Please, if there's one thing that you remember about derivatives, even if you don't remember the rules and all of that stuff after this class is over, please just remember that derivatives tell you about the speed. And it turns out that there's a lot of really, really useful things to know or that you can accomplish if you know the speed of a phenomenon of interest, right? That's what makes it a tool, is that knowing about the speed can tell you a lot of other things, like about the whole optimization stuff. But speed sometimes is itself a topic of interest. For example, to a traffic cop, the speed of vehicles is often the primary thing that they're interested in. They may not care about your trajectory itself, they just want to know if you're going the speed limit. So that's obviously sort of a very perhaps silly example almost, but this is why derivatives are both a tool and a topic of interest in themselves. If the speed is something that you care about, then it becomes a topic of interest, but in a lot of other situations, derivatives are just a tool. Okay, the next thing I'd like you guys to understand and to keep in mind, and you guys actually apply this often when you're working through derivative problems, but you may not be sort of really aware about this, is that derivatives are functions. So remember when I said that functions are used to model real-life phenomena? Well, if derivatives are functions, that means that derivatives themselves also model real-life phenomena. Right? And again, this gets at them not always only being a tool. Derivatives as functions can themselves be a topic of interest. All right, the fourth thing I'd like you guys to understand about tangent lines, we make a big fuss about finding the equation of a tangent line, right? Have all these different problems asking you guys to find the equation of the tangent line to this function at this point or whatever, right? Tangent lines, why do we care? Tangent lines are cool. And you'll be like, what do you mean they're cool? This is all sort of lame math stuff. And, the explanation I'll give about this might seem pretty lame to you guys as well. And, maybe it is. But to me, tangent lines are cool. And the reason why they're cool is because they approximate funky or strange curves with a simple line. Now, of course, this approximation gets worse and worse the further you get away from the point where you took the tangent line. But as long as you're close to that point, tangent lines do this really, really well. That was problem, I think it was number 3 from your take-home exam. Asked you guys to find an approximation for, I think it was the cube root of 28. The cube root of 28 is actually a number with an infinite number of digits that never repeat. You'd take forever to figure out all the digits of the square root of 28. But just by finding the tangent line to the function to the cube root function, you guys were able to get a pretty solid approximation of what the value of cube root of 28 is. And it didn't even take all that many steps to do. So that's why tangent lines are cool. You can approximate something really, really strange and funky looking with just a line as long as you stay pretty close to the point of approximation. That's pretty important stuff, and it's a pretty useful thing, I think, to have in mind when you ask yourself, why do we care about all these tangent line stuff? Now, last but not least, the last thing that I'd like you guys to understand about derivatives, and more specifically about optimization, and all that stuff. I think it's pretty clear by now why we do optimization, why we care about optimization, why this is useful in real life, right? We want to find the highest point. Cool. But the thing I'd like you to understand about optimization is that optimization works because of really creative use of the properties of derivatives. So remember the whole idea of the top of a hill is flat? That idea, which I went over and tried to emphasize so many times to you guys as being the reason why we do all this critical point business and all that process, it seems so simple. The idea to say that if you're at the top of a hill and your hill is nice and smooth, well, the top of the hill is flat, right? The same thing about the bottom of a valley is that it's flat there. It seems so simple, but just using that straightforward, very simple property about these points allowed us, if we just use that creatively, to develop a whole system of optimization in a really cool way, right? We didn't actually rely on all that much in order to be able to find these things, maxes and mins and all this stuff, that seems super important, right? We did this all by knowing about the speed. So I hope you guys can have at least some appreciation about sort of the creativity and the depth, in some sense, of what we're actually doing when we do this stuff. It seems really mechanical. It seems like we're just rehashing problems every time and all this. But behind the scenes in all these derivative problems, we're actually just finding really creative ways about using very simple information we have, which is just we know the speed. Cool. Derivatives tell us about the speed. Great. Speed is cool, I guess, right? But it turns out that just by knowing about the speed, you can do so much more, right? Tangent lines allow you to do very simple approximation, right? Just by knowing the speed, just looking for when the speed is 0, right? That's what finding critical points are, is just looking and finding where the speed is 0. It turns out that just by doing that, that allows you to find all of the candidate points for where your maximums and minimums can be. That's actually pretty crazy, right? there's something sort of cool and interesting and creative about the way that we're applying this pretty straightforward tool that's going on when we're using tangent lines in this way, when we're doing optimization problems, is it's not all that straightforward. And the fact that we can teach it in a class like this and make it seem almost boring is kind of crazy in a sense, right? Because if we didn't know how to do this stuff, if we were just developing this, this would seem really awesome, right? This would be like such an incredibly powerful new tool if you were just realizing that you can do this stuff like optimization just by knowing the speed, right? So hopefully this helps put into perspective a little bit what it is about derivatives that is so important, why somebody like me at least can get so excited about them, even if this stuff looks boring or feels kind of lame to you guys. But also what the sort of basic ideas are going on. Derivatives are just speed. That's all they are, right? They're functions in themselves. So they're a tool and they're a topic depending on the situation. But what they mean is just speed. That's all they mean. But it turns out there's so much that we can do just with the simple idea of being able to find the speed of a function. Just by being able to do that, there's so many cool applications and so many additional tricks and techniques that we can use just with this to get as much information about our functions as we possibly can. All right, with all that said, let's move on to part 3. And this was probably the shortest of the sections that we covered in this class, but it is, as far as calculus is concerned, an absolutely crucial section of calculus. From a mathematical perspective, calculus is 3 things. It's limits, its derivatives, and its integrals. And each of those 3 things is equally important. Now in this class, we don't cover limits. Limits are, remember I was telling you with derivatives that the rules allow you to avoid having to do all this fancy behind-the-scenes mathematical stuff. All that fancy behind-the-scenes mathematical stuff is limits. That's sort of slightly higher level, much more conceptual stuff. We don't talk about limits very much in this class at all. We have a big focus on derivatives, and we have some focus on integrals. But like I said, integrals is a core part of calculus, and it's the flip side of the coin. To derivatives. Right? On the one hand of the coin, you have derivatives, which tell you how to find the speed if you know the function. Integrals tell you how to find the original function if you know the speed. All right, so let's get into the material and topics, as well as the interpretation. And applications. So we didn't cover very much when it came to integrals, but we basically covered the definition. And remember that we have indefinite integrals, which are antiderivatives. And we have definite integrals. Which are the area under a curve. And then we went over some rules. We basically just went over the basic ones, which are the same as the basic rules, or at least the rules that we covered we covered the same types of rules as we covered for the basic rules section for derivatives, so I'm not going to relist all of those again. And then we covered the substitution technique, which is basically equivalent to chain rule. Okay. Now again, we didn't see all that much about this whole. Oh, well, there's one thing I don't want to forget about things that we covered. Let's see if I have some extra space here. Okay, so the other thing that we covered, this wasn't the last thing that we covered, but this is still very important, the fundamental theorem of calculus, or FTC. And recall that the fundamental theorem of calculus tells you basically that derivatives and integrals do the opposite thing. So if you do them one after the other, if you take the integral of the derivative, you end up roughly back where you started. And if you take the derivative of the integral, you end up also, again, roughly back where you started. Okay, so that's all the material that we covered as far as integrals are concerned. And I know that it doesn't seem like much, and we didn't have enough time or the opportunity, since basically all of integrals was covered through these video lectures. I think that a lot of the more conceptual stuff gets sort of lost in the process. And part of that's on me, not really having fully learned and still haven't fully mastered, I think, the way of doing these video lectures. But I do want to take some time now to go back over a little bit why these integral things are so important. And so the first thing that I'd like to mention is that area under curve actually allows us to find areas of lots of really cool shapes. So I say way more, and I mean way more than geometry class. So in geometry class, you guys learned how to find the areas of rectangles, of squares, of circles, of triangles, all this stuff. Just with definite integrals, finding the area under a curve, we can find the areas of so many different, really even funky and wild looking shapes just with this one tool. That's all you need, is just this one powerful tool of definite integration, and you can find all of these shapes. It sort of makes all of that geometry class stuff, well, geometry formulas are still pretty easy and straightforward. Probably easier to do these if you have just a rectangle. Probably easier to just use your formula for rectangles than to take an integral and all that. But we can do way more work with this than we could with just our geometry tools. That's the first thing, and I think that alone is worthwhile, right? It's worth keeping in mind that this is, just from a geometric perspective, pretty cool, right? A pretty powerful tool. The other thing that's important to keep in mind is that integrals they capture what we call accumulation or accumulated change. And this is maybe a bit more difficult to wrap your head around, like this idea of, what is this idea of accumulated change? It's not as straightforward as, derivatives was just speed or something, right? But this idea of accumulated change it's like they tally up. All the small, even technically infinitely small changes and variations to give you an end total. And this end total is exact. So this is, how to say, think about integrals as being like a really, really intense, souped up version of like a receipt, right? If you have a receipt, if you go to the restaurant, or I think nowadays it's probably more appropriate to say if you get takeout, right, from a restaurant, and you get your receipt itemizes for you all of the items that you purchased, right? You bought a salad, you bought some rice, you bought an entree, you bought some drinks, you bought all this stuff. And it tells you this one cost this much, this one cost this much, and it adds it all up into a bill, right? Very, very straightforward. We're basically just adding, right? Integrals do this for changes that are basically infinitely small in scale, right? Imagine if you had infinitely many things on your receipt that were all really, really tiny, right? Just tiny, 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 tiny price tags, but an infinite number of these. Integrals actually allow you to add those all up into a final tab in an exact way, even though you had infinitely many items. It's crazy. This stuff is really, really cool. But another way that you can think about this is as the reverse of the car, speed metaphor for derivatives is if you only know the speed of a vehicle throughout a road trip and you take the integral of that adds up all of the accumulated change in distance that you had from the speed, and it tells you how much distance you traveled at the end of the day, right? So if you look on your dashboard and you look at your odometer that tells you how many miles you've driven in your car, that's actually integrating the what you see on your speedometer, which tells you how fast you're going. So if you integrate your speed, you get the total mileage of your car. All right. Now, I understand this video has already been pretty long, but I'm going to wrap up this first section right now, the conceptual review, by just going over what you need to understand. About integrals. And the first thing is that they do the opposite of derivatives. And derivatives do the opposite of integrals. And this is the FTC. That's all the FTC says. Fundamental theorem of calculus, fancy, big fancy name. All it tells you is derivatives and integrals do the opposite thing from one another. That's what you need to understand about that. The second thing that you need to understand is that if you only knew the speed of a car throughout a road trip, integrating would give you the total distance traveled. This is very straightforward, but it tells you an idea of what integrals are doing, right? And the reason why integration is useful. We don't have any fancy optimization stuff with integrals. We can't find mins or maxes with them. That's why we don't spend as long on these as we do on derivatives in this class, right? But there's still something really, really useful about integrals, is that if you only know something about the speed, Integrating allows you to reconstruct the original function. And this is actually huge. It's actually difficult to really explain how incredible this is. Um, but this allows us to solve like a crazy amount of really strange problems, right? It turns out, you might not think this, but it turns out that there's a ton of physical, um, chemical, or all these other engineering problems where, I mean, you might not think it, but actually the only information about the phenomenon you're studying that you know is something about the rate of change. That's all you know. I know this sounds strange because it's hard to think of a situation in real life where you'd be so limited in your information as you are here. But it turns out that even in economics, in physics, in engineering, this happens quite a lot. That you only have information about the speed or about the derivative. And integrating allows you to reconstruct information about the process you started off with. And that in itself is pretty cool. Now, the third and last thing I'd like you guys to understand about integrals, and I really didn't go in depth about this, I'm not going to go into big detail, because this can get out of hand pretty quickly. But this is something that you might not learn about in your average math class or in your average textbook about integrals, is that you guys know how definite integrals take a curve and give you area? Right? We went over this. This is just seems very straightforward, right? Definite integral just gives you the area underneath a curve. Well, how many dimensions are each of these? A curve is 1D, right? And an area is 2D, right? So it gives you the area underneath a curve. Okay, now where am I going with this? Well, it turns out if you ever were to do any multivariable calculus or anything like that, I know you guys won't do any of that, but it turns out that this doesn't just apply to 1 to 2D. It turns out that they actually increase your dimension by 1. And I do mean dimension in the same way as we think about in space as being 3D. You're increasing the dimension by 1. So you can use definite integrals to go from 1D, just lines or curves, into 2D with area. But it turns out that if you were to get a bit fancier about this, you can actually do 3D to 4D. Now this is really crazy. None of us are capable at all in any way, shape, or form of understanding geometry in 4 dimensions. We can't see it because we live in a 3D world. But by using definite integrals, you actually could get an idea about things like hypervolume, geometry in 4 dimensions and stuff like that, which is really insane. But not only that, but you could go up from 4D to 5D, from 5D to 6D, all these situations, you're increasing dimension by 1. Now, I know this is sort of fancy, this is kind of a different type of thing to understand, but I'm hoping this gives you some insight into why definite integrals are so strong, is that it turns out when you do derivatives, you're actually dropping dimension down by 1. You're decreasing your dimension by 1, right? If you went from distance in miles, then speed is in miles per hour, right? You're dividing by the time. So you've decreased your dimension by 1. Integrals increase your dimension by 1 every time. So if you do these a lot, you can actually do some really insane stuff. And if you've ever looked at really cool or sort of mind-bending, crazy videos about like physics or stuff like that, telling you about how there's all these dimensions and all this stuff, I'm not a specialist in physics or anything of the sort, but I do know that there's a lot of weird dimensionality stuff that happens that's really fascinating, really interesting, and that's really cutting edge. And derivatives allow us to integrals rather, allow us to deal with all these extra dimension stuff. And it's a really powerful tool. You might not think when you just studied this pretty basic tool in this random math class with basically just a graduate student teaching you all this stuff, you might not think that this tool is all that impressive. But I wanted to mention this just to give you guys an idea of how strong and deep the the tools are that we're covering in this calculus course are. Why is calculus such a big deal? Is that this stuff gets really crazy. This is really, really, really powerful as a tool. Just the fact that you can increase your dimension by 1 when you're doing this gives you access to a whole world of possibilities that without calculus you wouldn't really be able to have any real idea how to even tackle. So even if we're just sort of barely skimming the surface here, and this is where I'm going to leave off for this video, I think. There will be, I'll be making, I promise you guys, a video going over all the types of problems that you need to cover for this course or need to know how to do for this course. I'll do that in a part 2 video. I'm not going to cover this all here. But hopefully this, just going over all this stuff, gives you guys an idea about why this course is something that's taught, why this course is something that's required of you guys, why this material is something that we think is worth teaching people, right? Why is it worth you guys learning this stuff? Why do we care? I hope this video gives you guys some idea of what the answers are to these questions. And I know that some of these answers may not be satisfying. You know, you may agree, you may not agree rather, that these reasons, all of these ideas or interpretations are a valid enough reason for you to care about math. But I can tell you that this is the reason why we teach this stuff. This is the reason why calculus is considered so important. And this is part of the reason why there are people like me who care enough about math and think math is cool enough of an activity that we actually dedicate, you know, a ton of years of study into learning more about this stuff. So hopefully this gives you guys a bit more of an idea of this. Hopefully you are able to understand at least some of the stuff that I've listed in this video and are able to take away some of this stuff at the end of this course, even after you're done with the final and with the class in general. You know, hopefully some of this stuff will stay with you. All right, I'm going to close out this video here. There will be a part 2 video going over the final exam review coming up right after this. All right.